Tonight, we're going to talk about the moon. Not about visiting it or planting a flag and coming home, but actually living there and building something permanent, raising children under a dome 239,000 miles from the nearest ocean. It sounds close. That's the trick the moon plays on you. You can see it without a telescope. It is close enough that we reached it with 1960s technology. But proximity has nothing to do with survivability. And when you start adding up everything the moon is missing, everything on that surface working against you, you begin to understand why we've never managed to stay. By the end of tonight, you're going to see why the moon that looks so close is, in almost every way that matters, completely hostile to everything you need to survive. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The moon is 239,000 miles away. 12 people have walked on it. The longest any of them stayed was about 3 days. The last one left in December 1972, and nobody has been back since. And yet, every time you see a proposal for a permanent lunar base, it's presented like the hard part is just getting there. It isn't, because staying is a fundamentally different problem from visiting. Visiting, you bring everything you need and you leave before it runs out. Staying means building an environment that can sustain you indefinitely, from scratch, on a world that is working against you in at least a dozen distinct ways simultaneously. This is what that actually looks like. Start with the most fatal problem. The moon has no atmosphere. Not a thin atmosphere. Not a damaged atmosphere. No atmosphere. The surface pressure is about 1/10 trillionth of what you're breathing right now, less than the best vacuum chambers we can build on Earth. If you stepped outside without a suit, your blood would begin to boil within seconds, not from heat, but from the sudden absence of pressure. The dissolved gases in your blood and tissues would rapidly expand. Nitrogen bubbles would form in your joints and your bloodstream. Your lungs would rupture if you tried to hold your breath. You'd lose consciousness in about 15 seconds. You'd be gone shortly after. Everything else that's hard about the moon, the radiation, the temperature swings, the dust, everything flows from this one fact. There's nothing between you and space. No buffer, no filter, no margin. So you build a buffer yourself. A lunar habitat has to maintain internal pressure at roughly 1 atmosphere of breathable air, while the outside is essentially nothing. That pressure differential creates enormous structural stress on every wall, every window, every seal. The habitat isn't just a building, it's a pressure vessel. Think of a submarine, a structure specifically engineered to maintain an internal environment radically different from the environment outside it. The submarine holds ocean pressure out. The lunar habitat holds vacuum out. The physics is similar. The consequences of failure are similar, and it has to hold for years without failure. A submarine goes on a mission and comes back. A lunar colony never comes back. Every seal, every weld, every joint has to survive indefinitely under continuous mechanical stress in a temperature environment that swings hundreds of degrees between lunar day and night. On Earth, a small crack in a wall is a maintenance issue. On the moon, it's potentially fatal. Slow decompression is survivable if caught early. That's what pressure sensors are for. A small leak can be patched if detected before the pressure drops to a dangerous level. Rapid decompression is a different problem entirely. The habitat also can't be too large, because every cubic meter of pressurized volume you build is mass you had to launch from Earth. Getting 1 kilogram into low Earth orbit currently costs somewhere between $1,000 and $3,000, depending on the rocket. Getting it to the lunar surface costs considerably more. The fuel cost alone to decelerate from lunar transfer orbit and touch down softly is substantial. Building a pressurized structure that can house dozens of people and run continuously for decades means launching an extraordinary amount of material across 239,000 miles. This is why every serious design for a permanent lunar base eventually circles back to the same idea: use what's already there. The moon has regolith a layer of broken, powdery rock covering the entire surface, in some places dozens of meters deep. Pack enough of it over your habitat and you solve several problems at once. Structural support from the weight above, radiation shielding from all that mass, thermal insulation from the extreme temperature swings on the surface. The regolith becomes your friend. But regolith isn't soil. We'll come back to that distinction. It matters more than you'd think. You need water to survive. You need oxygen to breathe. The moon appears to have neither. Appears to. In 2009, NASA crashed a rocket into a permanently shadowed crater near the lunar South Pole and analyzed the debris cloud. Water ice. Confirmed. The LC-ROSS mission, Lunar Crater Observation and Sensing Satellite, found water in concentrations up to 5.6% by mass in the excavated material, about the same as very dry desert soil on Earth. But it's there, and it's frozen, and it doesn't evaporate because those crater floors have never seen sunlight. This changes everything, in theory. Water ice can be split into hydrogen and oxygen. Through electrolysis, run electricity through it, and you get breathable air and rocket propellant. You can drink it. You can use it for radiation shielding, because water is excellent at stopping certain types of radiation. You can use the hydrogen and oxygen as fuel for spacecraft and rovers. A colony that can extract, purify, and use lunar water ice isn't entirely dependent on resupply from Earth for its most critical consumables, in theory. The problem is engineering at -390 degrees Fahrenheit or -234 degrees Celsius, in total darkness, inside a crater at the lunar South Pole. Those craters are permanently shadowed for a reason. They sit at the pole, where the sun skims along the horizon and never rises high enough to illuminate the crater floor. The sun has never shone on the bottom of some of these craters in billions of years. The water ice has been accumulating there since ancient comets and asteroids delivered it, preserved in the most effective deep freeze in the solar system. The moment you try to mine it, you're working in an environment that's colder than the surface of Pluto, that has no light, and your equipment was almost certainly not designed for those conditions. Machinery doesn't like that temperature. Lubricants freeze. Seals fail because materials contract differently at extreme cold, opening microscopic gaps. Electronics become brittle. Circuit boards can crack simply from thermal contraction. Batteries lose capacity precipitously in extreme cold. Every system that works perfectly in a lab at room temperature becomes a question mark at -390 degrees. And you need power to run the mining equipment. Power generated somewhere the sun can actually reach, which means running cables or relay systems from sunlit terrain down into the crater. More infrastructure, more mass, more failure points. The scale of this operation is also worth contemplating. A colony of 100 people might need hundreds of kilograms of water per day, factoring in drinking, cooking, hygiene, and agricultural use. Even at 5% concentration, that's a significant mining and processing operation, running continuously in the most hostile part of the lunar surface. The water is there, getting to it reliably, at scale. For a permanent colony, that's the engineering problem nobody has solved yet. And beyond water, there's oxygen. Earth's atmosphere is 21% oxygen. You could theoretically get oxygen from the water ice by electrolysis, as mentioned, but you could also extract it from the regolith itself. Lunar regolith is about 43% oxygen by mass, locked inside oxides of silicon, iron, aluminum, calcium, and titanium. The oxygen is there. Getting it out requires heating the regolith to extreme temperatures and running chemical reduction processes, essentially industrial smelting. But on the Moon, the European Space Agency and NASA have both demonstrated this in laboratory conditions. It works. But doing it at the scale a colony requires, with the reliability a colony requires, with locally manufactured spare parts. Because your supply line is 239,000 miles long, that's the gap between a proof of concept and an operational system. On Earth, you take energy for granted. The sun rises. The wind blows. Water flows. You can burn things. You have an endless, layered, redundant energy system that the entire biosphere runs on. And most of the time, you don't think about it at all. The Moon gives you one option with solar panels, and then it takes it away for 2 weeks at a time. A lunar day lasts about 29.5 Earth days. 2 weeks of sunlight. 2 weeks of darkness. For a solar-powered colony on the open surface, that's 14 days every month where your panels are generating nothing. 14 days where the temperature drops to minus 280 degrees Fahrenheit or minus 173 degrees Celsius, and everything in your colony has to run on whatever you stored. No battery technology currently available can store 2 weeks of power for a colony at reasonable mass and cost. The numbers simply don't work. A colony of 100 people, even with aggressive efficiency measures, might need several hundred kilowatts of continuous power. Store that for 14 days, and you're talking about energy storage on a scale that would require hundreds of metric tons of batteries, even with the best current technology. Launched from Earth. At thousands of dollars per kilogram. The math stops making sense quickly. 14 days of continuous power storage at meaningful scale would require a battery system so massive and so expensive that it negates the simplicity of solar panels in the first place. There are partial solutions. Some locations near the lunar poles, the peaks of eternal light, sit on elevated terrain where the low-angle sun illuminates them almost continuously. The geometry works out because these peaks are high enough to catch the sun even when it's barely above the horizon. Shackleton Crater Rim near the South Pole receives sunlight roughly 70 to 80% of the time. A habitat positioned there would face much shorter darkness periods. You still need storage for the gaps, but the gaps become hours, not weeks. The challenge is that the best places for solar power, the sunlit peaks, and the best places for water, the permanently shadowed crater floors, are separated by miles of terrain. You can't have both in the same spot. You'd need infrastructure connecting them. Power cables, rovers transporting water, relay systems. The more robust answer is nuclear power. A compact fission reactor doesn't care about the day-night cycle. It doesn't need sunlight. It generates power continuously, and 40 kilowatts, roughly what a small fission surface reactor could provide, is enough to run a meaningful outpost. NASA and the Department of Energy have been developing exactly this under the Fission Surface Power Program. A reactor designed to land on the Moon, deploy with minimal human intervention, and run reliably for at least 10 years. The technology is sound. Fission reactors have powered spacecraft before the SNAP reactors used on early American satellites, Soviet spacecraft that used them routinely, and more recently, the Kilopower project that demonstrated a small fission reactor in tests at the Nevada National Security Site in 2018. The design is advancing. But a nuclear reactor brings its own complexity. The radiation it produces has to be shielded from the colonists. A reactor on the lunar surface needs to be positioned at a sufficient distance or behind a physical barrier so that the neutron and gamma radiation it emits doesn't add to the already elevated radiation burden colonists are living with. Heat management in vacuum is counterintuitive. Space is cold, but a reactor generates enormous heat, and in vacuum there's no convection, only radiation. You need large radiator panels to dump the waste heat into space. The logistics of transporting fissile material, essentially a small amount of highly enriched uranium or plutonium off Earth, requires regulatory approvals, specialized handling, and safety systems for a potential launch failure. And if the reactor breaks down, you'd better have a spare or a repair plan, because your colony goes dark without it. Energy is solvable. On the Moon, nothing is simple. This is the one that surprises people. Lunar dust is not like dust on Earth. On Earth, dust is mostly rounded particles, grains that have been tumbled by wind, water, and time until their edges wear smooth. Earth dust settles, sweeps up, washes away. It's annoying. Lunar dust is something else entirely. Because the Moon has no wind, no water, and no geological activity to speak of, the particles on its surface have never been rounded. 4 billion years of meteorite impacts have pulverized the regolith into fragments with sharp, jagged, microscopic edges like tiny pieces of broken glass. Except they're measured in microns, and they're electrostatically charged. The charge is important. During the lunar day, ultraviolet radiation from the sun strips electrons from the surface, leaving the top layer of regolith positively charged. At the terminator line where day meets night, and in permanently shadowed regions, complex charging patterns create dust that actively levitates. Particles rise off the surface and drift horizontally, carried by the electric fields. They don't just settle on surfaces. They cling. An object set on the lunar surface doesn't just accumulate dust from above, like a car parked under a tree. The dust actively migrates to it, drawn electrostatically, coating every surface with extraordinary thoroughness. Apollo astronauts noticed this immediately. Harrison Schmitt, the only professional geologist to walk on the Moon, developed what he called lunar hay fever within hours of returning to the lunar module, sneezing, congestion, a reaction to the fine particles he'd tracked inside. The symptoms faded after a few hours, but the dust was inside the spacecraft, and it was inside his lungs. We don't fully understand the long-term health consequences of inhaling lunar dust. What we do know is that the particles are sharp. They don't degrade in the body the way rounded Earth dust does, and they may cause silicosis-like lung damage with extended exposure. Alan Bean and Pete Conrad, on Apollo 12, noted that after just a few hours on the surface, Their suits were visibly abraded. The dust was scratching the exterior layers of their equipment in a single EVA. An EVA that lasted about 3.5 hours. Imagine that happening to your spacesuit every day for years. The suit material designed to flex and move at the shoulder, elbow, knee, and hip joints while maintaining pressure, integrity degrades when abraded. Each layer of the suit serves a purpose. The outermost white thermal micrometeorite garment reflects sunlight and provides some protection against small impacts. Below that, multiple layers of aluminized mylar provide thermal insulation. Below that, the pressure bladder, which holds the atmosphere in, damage any of these layers and the suit's performance degrades. Seals around zippers and joints accumulate dust particles that prevent full closure. The tiny particles work into gaskets and interfere with the hermetic seal you need to maintain. Helmet visors scratch, reducing visibility and the effectiveness of the anti-glare coatings. Apollo missions lasted days. A colony means suits used repeatedly for years, and dust degradation means a suit certified for 500 hours of EVA might fail at 200. You'd need to maintain a supply of replacement suits, the components to repair them, and the manufacturing or delivery capability to replace them when beyond repair. Then there's the equipment outside the habitat. Solar panels, coated in dust, generate less electricity. Estimates suggest a thin layer of lunar dust can reduce solar panel output by 20 to 40% within months of deployment. The efficiency loss compounds over time as more dust accumulates. You need a cleaning strategy, and the dust clings electrostatically, meaning a brush doesn't work well. Moving mechanical parts, wheels on rovers, hinges on equipment panels, gears in machinery. The seals on airlocks accumulate dust in their mechanisms. The abrasion accelerates wear. A gear, designed to last 10 years on Earth, might last 3 on the lunar surface. The airlock is a particular challenge. Every time someone exits or enters the habitat, the airlock goes through a cycle: pressurization, depressurization, a physical transition zone where the suit coated in lunar dust is brought inside. You can design an airlock to minimize how much dust enters the habitat. You can install brushes, vacuum systems, electrostatic panels. But eliminating contamination entirely is nearly impossible. Over time, the habitat interior accumulates dust. The air filtration system has to be robust enough to capture particles down to the size of lunar dust particles as small as 1 to 2 microns, and do it continuously, because the lungs of the colonists can't afford to breathe what the air system misses. On Earth, dust is a nuisance. On the Moon, it's a slow, constant attack on every piece of equipment and every person that you depend on to survive. Research into electrostatic dust removal is ongoing. The concept is to use electric fields to repel the charged particles from surfaces, essentially fighting the electrostatic adhesion with electrostatic repulsion. Laboratory experiments have shown it works. Panels can be kept substantially cleaner when the electric field system is active. Whether it works at scale, in the real lunar environment, on surfaces of varied geometry, for years without maintenance failure, that's still an open question. It's one of the many things that needs to go from concept to operational reality before a permanent colony can function. Stand outside on a clear day. The reason you don't absorb a lethal dose of radiation in 30 seconds is that Earth has 2 layers of protection working simultaneously. First, the magnetic field. Earth's magnetosphere, the region of space shaped and dominated by our planet's magnetic field, deflects most of the charged particles streaming from the Sun before they reach the upper atmosphere. It's a planetary-scale shield, invisible and constant, generated by the motion of liquid iron in Earth's outer core. The Van Allen belts, discovered in 1958 by the first American satellite, are regions where the magnetosphere traps charged particles in two donut-shaped zones around the planet. The magnetosphere extends tens of thousands of miles into space in the direction facing the Sun, and stretches into a long tail in the direction away from it. It is, in effect, a buffer between Earth and much of what space throws at it. Second, the atmosphere. Even the particles that make it past the magnetosphere have to travel through roughly 65 miles of increasingly dense air before reaching ground level. Most of them don't make it. They interact with atmospheric atoms and molecules, losing energy, scattering, generating secondary particles that in turn scatter and lose energy. By the time anything reaches the surface, the most energetic and dangerous radiation has been substantially attenuated. The Moon has neither of these protections. No magnetic field worth mentioning. The Moon has a weak, patchy remnant magnetism in places, but nothing resembling a global magnetosphere. No atmosphere. What hits the surface hits it directly. The Chang'e 4 lander measured the dose on the lunar surface at roughly 1,300 microsieverts per day, which works out to somewhere around 400 to 500 millisieverts per year from charged particles alone. On Earth, the average person receives about 3 to 7 millisieverts per year from all sources combined: background radiation from naturally occurring radioactive materials in soil and rock, cosmic rays that make it through the atmosphere, medical imaging, and so on. For any given stretch of time, you absorb roughly 200 times more radiation standing on the Moon than standing on Earth. Extended exposure at lunar background levels would substantially elevate cancer risk over a lifetime. The numbers here aren't theoretical. Astronauts on the International Space Station, in low Earth orbit, where they're still partially protected by Earth's magnetic field, receive about 100 to 300 millisieverts per year, depending on the phase of the solar cycle. That's already elevated enough that NASA has career radiation dose limits for astronauts. The lunar surface is worse. Background radiation, though, is the manageable problem. The serious problem is solar particle events. When the Sun produces a major coronal mass ejection, a burst of high-energy charged particles, primarily protons, accelerated to significant fractions of the speed of light. Those particles can reach the Moon in as little as 10 to 20 minutes, and the bulk of them arrive within hours. A large solar particle event can deliver a dose of radiation to an unprotected person on the lunar surface that is measured not in millisieverts, but in Gray's units of absorbed radiation dose. A dose of a few Gray delivered to the whole body in a short period is acutely dangerous. Higher doses, delivered quickly, cause acute radiation syndrome, nausea, vomiting, damage to bone marrow, and the immune system. At very high doses, the outcome is fatal within days to weeks. The Carrington event in 1859 was the largest geomagnetic storm in recorded history. The solar particle event that accompanied it was so intense that aurora were visible from Cuba and Hawaii. Had humans been on the lunar surface with no shelter, the radiation dose would have been lethal for anyone caught outside. We cannot predict solar particle events far enough in advance to plan around them casually. We get warning. Solar monitoring satellites watch the sun continuously and can detect a coronal mass ejection as it occurs. But the particles arrive in minutes to hours. A colony needs a storm shelter, always accessible. A room designed specifically to offer the maximum radiation protection available, shielded by meters of regolith, or water, or polyethylene. Polyethylene and water are particularly effective at stopping the energetic protons that dominate solar particle events because they're rich in hydrogen atoms. Hydrogen is excellent at absorbing and scattering protons. When a high-energy proton hits a hydrogen atom, it loses a lot of its energy in a single collision. High atomic number materials like iron or lead don't do this as well. Every colonist needs to know where the shelter is. Every colonist needs to be able to reach it quickly. The shelter needs to be large enough to hold the entire colony and stocked with food, water, and oxygen for however long the event lasts. A major event can produce elevated particle flux for hours. Some last days. That shelter is not optional. It is as fundamental to lunar colony design as the pressure vessel itself. The deeper, subtler threat is galactic cosmic rays. These are high-energy particles originating from outside the solar system, the remnants of supernovae and other energetic events across the galaxy, accelerated to energies that dwarf what the sun produces. They come from all directions, all the time. The sun actually provides some protection against them. The solar wind creates a bubble called the heliosphere that partially deflects low-energy cosmic rays. But high-energy galactic cosmic rays punch through the heliosphere and hit the moon directly. Shielding against them is genuinely difficult. Heavy shielding dense materials like iron or lead actually makes the problem worse, in one respect. When a galactic cosmic ray particle strikes a heavy nucleus, it can produce a shower of secondary particles, a cascade of pions, muons, neutrons, and other fragments that spray out in all directions. Some of these secondary particles are biologically damaging in ways the original cosmic ray was not. This is called the fragmentation problem, and it means that simply piling lead around your habitat doesn't solve cosmic ray exposure. The optimal shielding against galactic cosmic rays is hydrogen-rich material again, water, polyethylene, plastics used at sufficient depth to stop both the primary particles and the secondary cascade without generating an unmanageable fragmentation event. Several meters of such material dramatically reduces the dose. But several meters of water, or polyethylene, is heavy, expensive to transport, and takes up space. The most practical solution remains the same one that addresses almost every radiation problem on the moon. Go underground. Bury your habitat under several meters of regolith. The soil isn't hydrogen-rich, but there's a lot of it, and quantity has its own merits. Several meters of lunar regolith reduces galactic cosmic ray flux by a meaningful factor. It's not perfect, but it's available, free, and already positioned over your lava tube if you're smart about where you build. Long-term radiation exposure on the moon is a solvable problem. It requires infrastructure, planning, and accepting that colonists will spend most of their time indoors. Even in well-shielded habitats, a lifetime on the moon carries a radiation burden that increases cancer risk. Exactly how much risk is acceptable, and who decides, and what compensation or acknowledgement colonists receive, those are questions that go far beyond engineering. They haven't been answered. In the 1960s, geologists and planetary scientists examining early lunar orbital imagery, noticed something odd. Long, sinuous channels called rills, some of which appeared to have partially collapsed roofs. The hypothesis was that these were ancient lava tubes. Billions of years ago, when the moon was volcanically active, rivers of lava flowed across its surface. As a lava flow cools, the exterior hardens first. It's exposed to the cold vacuum and loses heat relatively quickly. But the interior stays molten and keeps flowing. Eventually, the interior lava drains away, leaving a hollow tube beneath a solid roof. This same process happens on Earth. Hawaii and the Canary Islands have lava tubes you can walk into as a tourist. The lunar versions are likely much larger. On Earth, gravity is strong enough and the cooling fast enough that lava tubes rarely exceed a few meters in diameter. The moon's lower gravity and different eruption dynamics may have allowed lava tubes to form with cross-sections hundreds of meters across. In 2009, the Lunar Reconnaissance Orbiter photographed what appeared to be open pits, skylights, places where the roof of a lava tube had collapsed near Mare Tranquillitatis. One pit measured about 65 meters across at the surface. Thermal imaging data from the orbiter's Diviner instrument showed something remarkable. The interior of the pit maintained a temperature of around 63 degrees Fahrenheit, or 17 degrees Celsius, essentially constant, day and night. Regardless of whether the surface above was baking at 250 degrees in full sunlight or freezing at minus 280 degrees in the 2-week lunar night, the thermal stability is real and its cause is straightforward. The subsurface is insulated from the surface environment. Sunlight doesn't reach the interior. The temperature of the rock itself, set billions of years ago and maintained by the moon's residual internal heat and the insulating properties of the regolith above, sits at a comfortable level. For a colony, this has profound implications. Underground, you're insulated from the day-night temperature cycle. You're shielded from solar particle events. You're protected from micrometeorite impacts. No particle from space is getting through meters of solid rock. Your habitat structure faces no thermal cycling stress from the brutal surface temperature swings. And if the lava tube is large enough, and some may be, you have an enormous volume of potentially usable space without building the enclosure yourself. The moon may have left you a gift. The engineering challenge is sealing it. A lava tube opening, a skylight, is a hole in the roof. You'd need to construct an airtight seal across it. The pressurized habitat inside the tube needs walls, floors, atmospheric systems, power, lighting, all the infrastructure a colony requires. But the structural shell is already there. Instead of designing a dome strong enough to hold atmospheric pressure against the vacuum from outside, you're using a structure of rock that survived for billions of years. You're adding the guts, not building the body. There are open questions about structural stability. Lunar seismic activity, moonquakes, does occur. Some are caused by meteorite impacts. Others are tidal flexing from Earth's gravitational pull. Whether a lava tube can withstand decades of low-level seismic stress without section collapse is unknown. We haven't been inside one. We don't have structural data from the interior. But the concept is compelling enough that it appears in almost every serious long-term habitat proposal, and future robotic missions are being designed specifically to investigate these structures before any permanent settlement. Here's the problem that doesn't announce itself. Spend a year in zero gravity and the consequences are well documented. Bone density decreases at roughly 1 to 2% per month without aggressive countermeasures. The body interprets weightlessness as a signal that bone is unnecessary. Bone is metabolically expensive tissue, and if it's not being loaded by gravity, the body gradually reabsorbs it. Muscle atrophy proceeds in parallel. Without the constant work of holding you upright and moving you against gravity, the muscles responsible for posture and locomotion weaken. Astronauts returning from 6-month ISS expeditions often require rehabilitation to walk normally. The cardiovascular system adjusts to the redistribution of fluids in weightlessness. On Earth, your heart works harder to pump blood up to your head against gravity. In zero gravity, that demand disappears. The heart adapts, and the adaptation creates problems when gravity is reintroduced. Fluid shifts toward the head in microgravity, increasing intracranial pressure, causing a condition called space-associated neuroocular syndrome, SANS, that has measurably changed the shape of some astronauts' eyeballs, flattening them slightly from behind, and has degraded vision in ways that sometimes don't fully reverse after return to Earth. These effects are documented because astronauts come home and we measure them. 6 months in space, 1 year. We have data. Lunar gravity is 1/6 of Earth's. That's not zero. 17% of what you're experiencing right now. Some loading, some demand on bones and muscles and the cardiovascular system. The assumption that it's better than zero is almost certainly correct. But whether it's enough, whether 1/6 G prevents the long-term degradation that zero gravity causes, whether it causes its own distinct physiological changes, we genuinely do not know. No human being has spent more than 3 days in 1/6 gravity. The total time all 12 Apollo moonwalkers spent on the lunar surface combined is under 80 hours. That's 3 days and 8 hours, summed across all of them. We have no data whatsoever on what happens to human physiology over months or years at 1/6 G. This is not a gap that can be filled with theory. The body is complex enough that the only way to know what happens is to measure it. And we haven't, because we've never been there long enough. What minimum gravity is enough to maintain human health across a lifetime? We have never been able to answer that question because we have never had a subject population to measure. For a short-term outpost, this is an acceptable uncertainty. You accept some degradation, you implement countermeasures as best you can, and you bring people home before the effects become irreversible. For a permanent colony, where people are not coming home, it becomes one of the most pressing medical unknowns in the entire enterprise. If colonists' bodies degrade meaningfully under lunar gravity, even with aggressive countermeasures, regular exercise, carefully designed resistance programs, monitoring you have a medical crisis building slowly in everyone, all the time, and there may not be enough medical infrastructure to address it. The darker implication is for the next generation. A child born on the moon, raised from infancy in 1/6 gravity, would develop bones, muscles, and a cardiovascular system calibrated to that environment. Not as a dysfunction, as a normal adaptation. The body is remarkably plastic, especially in childhood. It optimizes for the demands placed on it. A child who grows up in 1/6 G would optimize for 1/6 G. Their skeleton would develop with the loading patterns of 1/6 G as the baseline. Their heart would develop for the cardiovascular demands of 1/6 G. Their muscles would develop in proportion to what 1/6 g requires. And the adaptation that makes them healthy on the moon might make them unable to tolerate Earth. Full Earth gravity, 6 times what they've experienced, might be crushing to a body that never prepared for it. Their bones might not be dense enough. Their heart might not be strong enough to move blood against the full weight of Earth. Their muscles might not sustain their own weight. A generation raised on the moon may be physically incapable of returning to Earth. Not by choice, not by economics, by biology. That's not a catastrophe, necessarily. Humanity has always adapted to the environments it lives in. People born and raised at high altitude have subtly different physiology from people born at sea level. Different red blood cell counts, different lung capacities. They're the same species, but they're adapted to their environment. Lunar humans, across generations, might become something similarly distinct, adapted to their world, functional and healthy within it, but unable to visit the origin world. It's worth being clear-eyed about what that means before the first children are born under a dome at the lunar South Pole. The moon has no soil. This sounds obvious, but the implications run deep. Soil is not just dirt. Soil is a living system. Earth's topsoil contains bacteria, fungi, archaea, nematodes, earthworms, and a web of chemical relationships built over millions of years that allow plants to extract the nutrients they need from the ground. A handful of healthy agricultural soil contains more individual organisms than there are people on Earth. The fungi, called mycorrhizae, form networks connecting plant roots and allowing the exchange of nutrients across distances. The bacteria fix nitrogen from the air into forms plants can use. The organic matter, decaying leaves, animal waste, dead organisms, provides a continuous supply of nutrients cycling through the system. Soil is infrastructure, ancient, living infrastructure built by billions of years of evolution. Lunar regolith is none of that. It's crushed rock, inorganic, sterile. The regolith also contains things actively hostile to plant life. Solar wind particles have been implanting hydrogen, helium, and trace heavy metals into the surface grains for billions of years. Some of those trace metals, chromium, nickel, are toxic to plant roots in high concentrations. The regolith also lacks the nitrogen and phosphorus compounds that terrestrial plants need. And the physical structure is wrong. The sharp, glassy particles don't create the pore structure that allows plant roots to breathe. In 2022, a team of researchers at the University of Florida grew plants in actual Apollo-returned lunar samples. Seeds germinated. Plants grew. This was a remarkable result, the first time anything had ever grown in real lunar material. But the plants were stressed. They grew slower and smaller than controls in ordinary soil. Their gene expression showed activation of stress response pathways. They were surviving in the regolith, not thriving. And those were seedlings in a carefully controlled laboratory environment, monitored closely, given ideal conditions for everything except the growth medium. A colony doesn't get ideal conditions. It gets the real environment. The practical food solution for a lunar colony isn't farming regolith. It's hydroponics and aeroponics, growing plants in controlled environments where nutrient-rich water is delivered directly to the roots, with no soil required. In hydroponics, roots hang in or are periodically flooded with nutrient solution. In aeroponics, roots are suspended in air and misted with nutrient solution. Both approaches can be extraordinarily productive per square meter. Without the physical constraint of soil, you can stack growing trays vertically, multiplying the productive area per floor area. LED lighting has become efficient enough that the energy cost of illuminating growing chambers is no longer prohibitive. Modern agricultural LEDs, tuned to the wavelengths plants use most, can deliver photosynthetically active radiation at much lower energy cost than earlier systems. But the math is still sobering. A person requires roughly 2,000 calories a day, providing that from indoor-grown plants requires approximately 80 to 100 square meters of growing area per person under optimal conditions. This is an optimistic estimate based on high-yielding crops like sweet potatoes, wheat, and leafy greens, grown under ideal conditions with experienced management. For 100 colonists, you need somewhere between 8,000 and 10,000 square meters of pressurized, lit, heated, climate-controlled agricultural space. That's roughly 108,000 square feet of growing floor. All of it heated. All of it lit. All of it pressurized. All of it managed. All of it subject to the same dust contamination, maintenance requirements, and system dependency as every other part of the colony. A plant disease outbreak in a closed agricultural system where there are no birds or insects to serve as biological controls and no outdoor environment to provide dilution, could spread through an entire growing chamber in days. Crop failures in a system with no food imports and no stockpile of more than a few months are existential events. And the agricultural system has to be closed loop. On Earth, the nutrients in human waste eventually return to the soil through sewage treatment, composting, and the natural cycling of matter. A lunar colony has to replicate this deliberately. Human waste is fertilizer. The nitrogen, phosphorus, and potassium in human metabolic output have to be captured and processed and returned to the growing system, or you're constantly importing replacement nutrients. Water, evaporating from plant surfaces, has to be captured condensed from the air in the growing chamber and recycled back into the nutrient delivery system. Every input that isn't recycled is a supply line. Every supply line is a vulnerability. The closed-loop food system that a truly permanent lunar colony requires is one of the most complex engineering challenges in the entire project. And it's also one of the most poorly understood, because nothing like it has ever been operated at the scale required for a large population. The longest-running closed ecological systems experiments, things like the Biosphere 2 project in Arizona in the early 1990s, ran into serious problems. Oxygen levels dropped unexpectedly. Populations of some species crashed. Others exploded. The system was not as self-regulating as hoped. The lesson from Biosphere 2 is not that closed ecological systems are impossible. It's that they're more complex and more fragile than they appear, and that you don't understand all the failure modes until you're inside one. A lunar colony will be inside one. The engineering problems are the ones that get discussed in papers and proposals. They're the ones that get funded and modeled and prototyped. But the history of isolated human communities, Antarctic research stations, submarines, long maritime expeditions, early polar camps consistently shows that the hardest problems aren't always the technical ones. People are complicated. The Concordia station in Antarctica offers a useful data point. It's staffed year-round by a small crew of about 12 to 15 people. isolated during the polar winter for roughly 9 months, when weather conditions make resupply and evacuation nearly impossible. The station runs scientific programs, conducts medical research, and perhaps most valuably for space exploration, serves as a proxy for the psychological conditions of an isolated, long-duration mission. Studies of Concordia crews document something researchers call the third quarter phenomenon, a consistent dip in morale, motivation, and cognitive performance that appears roughly 2/3 of the way through a deployment. Around the 7 or 8 month mark, in a 9-month deployment, people become irritable. Minor interpersonal conflicts that were manageable earlier in the deployment escalate. Depression is more common. Cognitive performance on certain tasks measurably declines. This happens even in carefully screened, psychologically resilient, professional personnel who knew what they were signing up for and have a fixed end date they're counting down to. Concordia is in Antarctica. The crews know they're going home. They have that end date. They have emergency rescue available, albeit difficult to execute in winter conditions. Their families are on the same planet. Now, remove the fixed end date. Make the deployment permanent. Put the habitat 239,000 miles away. Eliminate the possibility of emergency evacuation. A return trip to Earth from the Moon takes 3 days and requires a functioning spacecraft, which may or may not be available or ready at the moment someone needs to leave. Make clear that coming back, if possible at all, requires substantial resources, planning, and months of lead time. A permanent lunar colony isn't a deployment. It's a life. The governance structure, the conflict resolution mechanisms, the mental health support systems, the social architecture of a community that must function indefinitely in an enclosed environment, none of that comes automatically from the engineering designs. You can build a perfect pressure vessel and still watch it tear itself apart from the inside. The colony needs some form of governance. Someone, or some group, makes decisions about resource allocation, conflict resolution, housing assignments, work schedules, and what happens when people fundamentally disagree. Democratic governance requires mechanisms, voting systems, representation, enforcement. Authoritarian governance creates its own problems in a community of people who came voluntarily and have strong feelings about their situation. Whatever system is chosen, it has to function when things are going wrong, under stress, when resources are scarce, when someone is injured and the colony has to change its routines to accommodate, when 2 people cannot stand each other and they're in a habitat with 100 other people and there is nowhere to go. Psychology and social dynamics have been part of the Antarctic research program for decades. The lessons from that research are increasingly influencing long-duration space mission planning. But a lunar colony is not a research station. The people there didn't sign up for a defined term. They have no departure date. That changes the psychology in ways we don't fully understand because we've never had a group of people in that situation. Private space in a pressurized habitat is expensive. Every square meter of enclosed volume is mass you launched from Earth, power you have to heat and light and maintain. Giving each colonist a private room, a door they can close, a space that is genuinely theirs requires accepting that as a design priority and paying the cost. But the evidence from isolated community studies is consistent. People need private space. They need the ability to be alone. The ability to separate from other people is one of the coping mechanisms humans use to regulate interpersonal stress. Remove it, and the stress accumulates. None of this is insurmountable, but it requires building the social infrastructure as deliberately as the physical infrastructure. The psychological health systems, the governance mechanisms, the conflict resolution processes, these are as much part of the colony design as the water recycling system or the power plant. They just don't fit neatly into an engineering proposal. Medical capability is one of the starkest differences between an Earth city and a lunar colony. On Earth, the healthcare system scales. A general practitioner handles minor issues. A regional hospital handles moderate complexity. A major academic medical center handles the most challenging cases. And at every level, if the current level isn't enough, you transfer the patient to the next level up. You escalate. You always have somewhere to escalate to. On the Moon, the medical capability available is the medical capability that was brought there and maintained there. That's the ceiling. There is no escalation. There is no transfer. A patient who needs a level of care beyond what's available at the colony either gets improvised treatment or they don't get treatment. Consider the range of medical emergencies that can occur in any group of people. Appendicitis, cardiac events, heart attacks, arrhythmias, stroke, traumatic injury from accidents, a fall in 1/6 gravity, an equipment malfunction, a depressurization event, cancer, which requires chemotherapy, radiation therapy, or surgical intervention depending on the type and stage, childbirth complications, psychiatric emergencies, a dental abscess that becomes septic and life-threatening if untreated, kidney stones, sepsis. Any of these can happen to any human being. On Earth, you have hospitals. On the Moon, you have whoever the colony brought with medical training, whatever equipment was launched from Earth, and whatever medications were included in the manifests. Performing surgery in 1/6 gravity introduces complications that haven't been fully worked out. Fluids, blood, irrigation fluids, the contents of internal organs behave differently under 1/6 G than under full gravity. Procedures that rely on fluids settling in a predictable direction don't work the same way. Equipment designed for Earth operating theaters assumes a gravitational environment that affects everything from how instruments lie on a tray to how anesthesia distributes in the body. Anesthesia physiology in partial gravity is not well characterized. We don't know if drug dosing needs to be adjusted, how ventilation management differs, how recovery from anesthesia proceeds. These are not small questions to leave open. Every colonist would need medical training far beyond what any civilian carries today. Not just first aid. Surgical first responder training. Emergency medicine. Wilderness medicine adapted for a context where the wilderness is a vacuum and the nearest help is a 3-day spaceflight away. The colony's designated medical personnel, one person, ideally, more can't rely on consultation with specialists on Earth, except by the time-delayed text or video link that reaches 239,000 miles. 1.28 seconds each way. Real-time communication is possible, unlike Mars. But the specialist on Earth can offer guidance, not hands. They can advise the colonist performing the procedure, but they can't perform it. Pharmaceutical management adds another layer of complexity. Drugs degrade. Some remain effective, well past their labeled expiration date. Studies of medications stored in optimal conditions have found them effective for years, beyond expiration. Others degrade on schedule, becoming inert or occasionally dangerous. A colony needs a pharmaceutical inventory with known shelf lives, a resupply schedule that ensures critical medications don't expire before replacements arrive, and the capacity to manage medications across a population of 100 or more people with varied health needs across years or decades. Some medications require refrigeration. The power supply for pharmaceutical refrigeration is part of the life support system. If the power goes out, the medications go bad. If the specific medication a colonist needs wasn't on the manifest, because nobody anticipated that particular medical need, it doesn't exist at the colony. The medically self-sufficient lunar colony is orders of magnitude more complex than a colony that simply has a doctor on staff. It may ultimately require a manufacturing capability for essential medications, using chemical synthesis from raw materials. That's an entire, additional industrial system. The people working on permanent lunar colony design are increasingly including medical systems specialists in the planning process. This is relatively recent. Early concepts were almost entirely physics and engineering. The biological and medical requirements are now recognized as constraints on design decisions, not afterthoughts. On Earth, everything falls apart slowly. You paint a house and it weathers. You leave a car and the rubber in the tires oxidizes. You abandon a building and the seasons crack the concrete. Entropy is real, but on Earth, it moves at a rate calibrated to Earth conditions. Wind and rain and microorganisms are the agents of decay, and they work on timescales of decades. On the Moon, the agents of decay are different, and some of them are faster. Radiation, thermal cycling, micro-impacts, vacuum-induced material changes. The electronics in a lunar colony are constantly being bombarded by cosmic rays and solar radiation. Each high-energy particle passing through a microchip deposits some energy. Over time, this creates what engineers call cumulative radiation damage, bit errors in memory, altered behavior in transistors, eventual component failure. Electronics designed for space applications are radiation-hardened, manufactured with larger transistor geometries, protective design features, and sometimes shielded packaging. But radiation hardening has limits. Every component in a lunar colony has a finite radiation tolerance. After enough cumulative dose, they fail. The thermal environment accelerates material degradation in a different way. The surface of the Moon swings between roughly 250 degrees Fahrenheit or 121 degrees Celsius during the day, and minus 280 degrees Fahrenheit or minus 173 degrees Celsius at night. Even inside a pressurized habitat with climate control, the structural elements of the habitat experience temperature differentials. Joints between materials with different thermal expansion coefficients flex slightly with each cycle. 2 weeks of expansion, 2 weeks of contraction, repeated indefinitely. The seals around windows and penetrations where cables or pipes pass through the habitat wall are particular concern. Each thermal cycle stresses the seal slightly. Over years and decades, this fatigue accumulates. The seal that was rated for 5,000 thermal cycles may begin to show micro-leakage at 8,000. The polymer materials used in gaskets, O-rings, and flexible seals degrade under ultraviolet radiation and vacuum exposure even before thermal cycling is considered. On Earth, A rubber gasket is replaced when it shows signs of wear. On the Moon, replacement requires either having a spare in inventory launched from Earth or manufacturing one locally. Every failure mode in a lunar colony has one of three resolutions: repair it with what you have, manufacture a replacement from available materials, or accept that the system no longer works at full capacity. The ratio of maintenance work to productive work in a lunar colony is likely higher than any Earth analogy would suggest. In early terrestrial colonies, historians estimate that a majority of time was consumed by the basic work of survival, food production, shelter maintenance, water management. A lunar colony faces a similar situation, compounded by the fact that the technical complexity of what's being maintained is incomparably higher. A colonist who spends their morning repairing a seal on an airlock hinge, their afternoon monitoring the atmospheric recycling sensors, and their evening logging dust accumulation data on the solar panels is not doing science or engineering. They're keeping the habitat alive. And keeping the habitat alive is the job that never stops. On Earth, space debris burns up. Every day, roughly 100 metric tons of material enters Earth's atmosphere: dust, pebbles, the occasional larger rock. The vast majority of it never reaches the ground. The atmosphere intercepts it, friction heats the particle to incandescence, and it ablates away in the streak of light you see on a clear night and call a shooting star. The Moon has no atmosphere. What hits the surface hits the surface. Micrometeorites, particles ranging from a few microns to a few millimeters, strike the lunar surface constantly. The rate of impact on any given square meter of the surface is estimated at tens of thousands per year for the smallest particles, dropping off steeply as particle size increases. Most of these impacts are imperceptibly small. A grain of dust hitting the surface at 30,000 miles per hour creates a tiny crater measured in microns. But even small particles at those velocities carry meaningful kinetic energy. A particle 1 millimeter across, at typical micrometeorite velocities, carries roughly the same energy as a rifle bullet in the small particle regime. For a pressure vessel, this matters. A habitat wall that develops a micrometeorite penetration isn't a theoretical concern. It's a probability that accumulates over time. The longer the colony operates, the larger its cross-sectional area of structures exposed to the surface environment, and the higher the cumulative probability of a meaningful impact. Habitat designs use Whipple shields, layers of material separated by spacing, where an impacting particle strikes the outer bumper layer, fragments and disperses its energy, and the expanded cloud of debris then has to penetrate the inner wall. A particle that would punch straight through a single layer of aluminum instead spreads its energy across a larger area of the inner wall, dramatically reducing the penetration probability. This design is used on the ISS and on spacecraft generally. But a lunar colony is not a spacecraft. It's a permanent installation with a much larger exposed area, operating continuously for decades. The math of cumulative probability becomes uncomfortable over long timescales. A 1 in 10,000 chance of a damaging impact per year, per module, sounds reassuring. A colony with 50 modules, operating for 50 years, is facing a very different probability landscape. Underground habitats solve this cleanly. Under several meters of rock, micrometeorites are irrelevant. They hit the surface above you, create their tiny craters, and their energy dissipates in the regolith. Nothing reaches you. This is another argument for lava tube habitation or deeply buried surface structures. For surface structures that can't be underground power systems, mining equipment, antennas, airlocks micrometeorite protection requires ongoing assessment and maintenance. External surfaces get inspected. Damage gets repaired. Vulnerable components get replacements scheduled before failure rather than after. It's a manageable problem. But it's a problem that requires continuous attention across the entire life of the colony, and that attention costs crew, time, and resources. The Moon's communication situation is, by space exploration standards, relatively manageable. Radio signals travel the 239,000 miles between Earth and the lunar surface in about 1.28 seconds. Round-trip delay of 2.56 seconds. That's enough to make real-time conversation slightly awkward, a noticeable pause between speaking and hearing the response. But it's nothing like the 20-minute, one-way delays that would characterize communication with Mars during a significant part of its orbit. You can actually talk to people on the Moon, not as smoothly as a phone call. But you can have a real conversation. This is genuinely important for the psychological dimension of the colony. Isolation from Earth is real, but it's not the isolating silence of a Mars mission. Colonists can call home. They can video conference with family. They can watch live events, receive news as it happens, consult with experts in real time. That contact doesn't solve the psychological challenge of permanent relocation, but it makes it meaningfully different from what Mars colonists will face. The technical challenge is infrastructure. Communication from the lunar South Pole, where the water ice and favorable solar conditions make it the likely site of a first colony, requires either line of sight to an undercell, Earth-facing relay satellite, or a direct antenna geometry that allows transmission. The South Pole isn't on the near side of the Moon, which always faces Earth. It's at the edge, where the geometry is challenging. Relay satellites in lunar orbit are the standard solution. Park a satellite or a small constellation where they can see both the South Pole and Earth simultaneously, and route communications through them. The Lunar Gateway space station, planned for a near-rectilinear halo orbit, is designed in part to serve this relay function. But relay infrastructure is itself something that has to be launched, maintained, and operated. More systems, more failure modes. Inside the colony itself, communication is a different engineering challenge. A large underground facility, potentially spread across multiple lava tube sections, needs an internal network. You can run fiber optic cables, glass fibers, that carry data as pulses of light through the habitat. Glass is robust in the lunar environment in ways that electronic systems are not. But fiber requires careful routing and protection against the mechanical stresses of a working habitat. Wireless communication inside a metal-walled pressure vessel behaves differently than in open-air signals. Bounce, interfere, create dead spots. The internal communication network of a lunar colony is a serious engineering design consideration, not an afterthought. And the network has to support not just voice and video, but the telemetry from thousands of sensors monitoring every aspect of the habitat's condition. Pressure sensors, atmospheric composition sensors, temperature sensors, dust accumulation sensors, radiation dosimeters, power system monitors, water quality sensors, agricultural system monitors. A modern lunar colony would generate an enormous quantity of sensor data every second. processing and acting on that data, determining what's normal, what's anomalous, what requires immediate attention, is itself a significant task. Automated systems handle the routine monitoring. Human operators handle the exceptions. Defining the boundary between routine and exception, and building systems robust enough that the exceptions are rare, is another layer of engineering complexity. In a sealed, pressurized environment, fire is a threat of a different character than it is outdoors. On Earth, a fire has somewhere to go. It produces smoke and combustion gases that disperse into the open air. You can move away from it. The fire department comes. In a sealed habitat, combustion gases, carbon monoxide, carbon dioxide, particulates, and the chemical byproducts of burning synthetic materials accumulate in the shared atmosphere. There is no outside. The atmosphere the fire is polluting is the same atmosphere everyone in the colony breathes. Carbon monoxide is particularly dangerous because it's colorless, odorless, and causes incapacitation before the person affected realizes anything is wrong. Concentrations that would be merely concerning outdoors are potentially lethal in an enclosed space. The ISS has had fire incidents. In 1997, an oxygen-generating canister on the Mir space station caught fire and burned for about 14 minutes, filling the station with smoke. Crew members had to don oxygen masks. The incident highlighted how dangerous fire is in an enclosed space environment. Lunar habitat design has to take fire risks seriously throughout. Material selection is constrained by flammability. On Earth, you use the most functional material for each application. In a pressurized habitat, you add flammability to the evaluation criteria. Certain polymers that would be structurally ideal are eliminated because they burn too readily or produce toxic combustion products. Everything that can be made of metal or fire-resistant composite is. Fire suppression systems have to work in a sealed environment without making the atmosphere unbreathable themselves. The traditional response of flooding an area with water is problematic in electronics-rich environments. Halon gas systems, once common in aircraft and ships, are effective at suppression, but toxic to humans at sufficient concentration. Carbon dioxide systems suffocate occupants if the concentration gets too high. The current standard on spacecraft is fine water mist or aerosol suppression. Extremely fine water droplets that extinguish fires with less water than traditional sprinklers, protecting electronics better and not creating an oxygen displacement hazard. These systems work. But they require design integration throughout the habitat, maintenance, and periodic testing. They're another system that has to function reliably across years of operation. Habitat section isolation is also part of the fire safety architecture. If a section catches fire, the adjacent sections need to be isolatable, sealed off with fire-resistant bulkheads and independent atmospheric systems, so the rest of the colony isn't contaminated. This means the habitat's physical architecture incorporates compartmentalization as a design requirement, not an option. Compartmentalization adds complexity. It adds weight. It adds seals that have to be maintained. But a fire in a non-compartmentalized sealed habitat is potentially catastrophic for everyone inside. The design priority is clear. The lunar colony is, for the foreseeable future, dependent on Earth. Not for everything, eventually. But in the early decades, for many things. Specialized electronics, medications, equipment with complex manufacturing requirements. materials that can't yet be produced from lunar resources, replacement components for systems that haven't yet been locally replicated. The supply chain from Earth to the Moon is unlike any supply chain on Earth. Transit time is about 3 days. But launch windows, the times when orbital mechanics make a given mission trajectory efficient, occur at regular intervals, not on demand. A resupply ship doesn't launch the day you realize you need something. It launches when the mission is planned, the vehicle is ready, and the launch window is open. The realistic cadence for a permanent lunar colony, at least in early phases, might be several resupply missions per year. Each one represents a fixed opportunity to receive critical supplies. Miss the manifest deadline for something you need, and you wait for the next window. Identifying what you'll need 3 to 6 months from now, in a dynamic environment where requirements change based on equipment failures and consumption rates and the health needs of the population, is a supply chain management challenge of the first order. And the supply chain has a dependency beyond logistics. It depends on the continued political will and financial commitment of the entities supporting it. Earth's history of ambitious remote outposts includes many examples of supply chains that were cut, bases abandoned when budgets tightened, expeditions recalled when political priorities shifted. A lunar colony that depends on a supply chain from a single national space agency or even a single commercial operator is vulnerable to changes in that institution's priorities. The resilience of the colony over decades requires either achieving food and basic materials, self-sufficiency, or having a supply chain sufficiently diverse and committed that it's unlikely to be interrupted. Neither of these is easy to guarantee. The stockpile strategy, maintaining enough reserve of every critical consumable to survive interruption of supply for 6 months or a year or 2 years, is one approach. But stockpiles require storage space, which requires pressurized volume, which requires mass launched from Earth. Every month of emergency reserve is a cost paid up front. The path to self-sufficiency is the more robust, long-term answer. And the path runs through all the industrial and agricultural challenges described throughout this script: mining, refining, manufacturing, food production, energy self-sufficiency. Each capability developed makes the colony more resilient. Each one takes years to develop and prove. The trajectory from dependent outpost to independent settlement is measured in decades, even under the most optimistic assumptions. Living on the Moon is one challenge. Working on the Moon is another. Science, construction, maintenance, mining, all the activities that justify and sustain a colony require going outside. And outside means a spacesuit. Apollo's spacesuits were engineering masterpieces, but they were designed for missions measured in hours and days. The suits used on Apollo were single mission items. Not entirely, they were worn multiple times during the mission. But they were not designed for hundreds of reuse cycles over years. A lunar colony requires suits that can be suited up, evade, desiccated, and stored, then done again, repeatedly, for years. The current generation of exploration spacesuits being developed for Artemis, including the Axiom Space and Collins Aerospace, designs under contract to NASA, represent a significant advancement over Apollo-era suits. Better mobility at the shoulder. More intuitive donning and doffing. More robust life support. But they still face the fundamental problem. The lunar environment degrades them. Every EVA deposits dust on the suit. Every movement flexes the joints and advances the abrasion. Every thermal cycle stresses the materials. A suit designed for a 250-hour operational life is not adequate for a colonist who needs to EVA regularly for years. Developing suits that can withstand 1,000 or more hours of lunar surface use, or that can be maintained and repaired to extend their service life, is an active area of development that hasn't reached satisfactory resolution. The suits also constrain what work can be done. A pressurized glove that maintains atmosphere while allowing fine motor manipulation is an extraordinarily difficult engineering compromise. Squeeze the suit tightly enough to allow finger dexterity, and it becomes impossible to maintain against suit pressure. The suit's internal pressure continuously tries to straighten the fingers and open the hand. Every Apollo astronaut who did significant EVA work reported hand and forearm fatigue. The grip strength required to operate tools against suit pressure is exhausting. Precision work, delicate assembly, careful sampling, fine instrument adjustment is genuinely difficult in a pressurized glove. A colony that requires skilled technical work outside the habitat is going to struggle with the dexterity limitations of pressurized suits. The answer might be increased automation and robotics for surface operations. Robots can be designed for the lunar environment without the biological constraints of a pressurized suit. They don't need to breathe. They don't get cold. They don't fatigue. Robotic systems are increasingly capable. The state of autonomous manipulation and terrain navigation has advanced considerably since the Apollo era. But robots require maintenance, programming, repair when they fail, and supervision for complex or novel tasks. They're tools, not replacements for human judgment in all situations. The mix of human EVA and robotic operations that a mature lunar colony would use is still being worked out. Rovers extend the range of surface operations significantly. A pressurized rover, one with a cabin that maintains atmosphere, so the crew inside doesn't have to wear suits, for the journey could allow colonists to operate tens of miles from the base. The unpressurized rover range is limited by how long colonists can work in suits, suit consumables, and the need to return before something goes wrong. A pressurized rover changes the equation substantially. Apollo used small, open, electric rovers on the last 3 missions. They extended exploration dramatically, but were still limited to relatively short journeys from the lander. A pressurized rover, capable of multi-day traverses, with sleeping accommodations and its own life support, would allow geological surveys, resource prospecting, and infrastructure installation across a much larger region. The design, construction, and maintenance of that rover fleet is another system requirement for a mature colony. Wheels and treads accumulate dust. Drive motors and transmissions need maintenance. Power systems need to carry enough energy for a multi-day traverse and return. Communications need to reach back to the base, possibly through relay systems if the terrain is between you and your antenna. Navigation across terrain that has no GPS. The moon doesn't have a satellite. Navigation system requires either visual navigation by the crew, dead reckoning from odometry and heading, or a lunar positioning system established as part of the colony infrastructure. NASA and ESA have both proposed lunar navigation satellite systems modeled on GPS. They don't exist yet. Operating on the surface without them is possible. It requires more crew attention and is more prone to navigational error. Building the navigation infrastructure is on the to-do list for a permanent lunar presence. The list is long. The thermal environment on the lunar surface is one of the most extreme anywhere we've found in the solar system. More extreme, in some ways, than either of the most commonly mentioned alternatives for human habitation. The surface of Mars gets cold, sometimes very cold, approaching -220 degrees Fahrenheit or -140 degrees Celsius, near the poles in winter. But it has an atmosphere. Thin as Martian air is about 1% of Earth's pressure, it still provides some thermal buffering. The surface of the Moon has no buffering at all. At the equator, the sunlit surface reaches about 250 degrees Fahrenheit or 121 degrees Celsius during the day. The same surface, after 2 weeks in darkness, drops to about -280 degrees Fahrenheit or -173 degrees Celsius at night. A swing of more than 500 degrees Fahrenheit or 260 degrees Celsius between the same location's day and night temperature. No material system handles that gracefully without design consideration. Metals expand and contract with temperature. Different metals expand at different rates, so joints between dissimilar metals experience shear stress during every thermal cycle. A joint that's tight at 250 degrees has a different geometry at -280. Bolts loosen. Gaskets compress unevenly. Welds develop microfractures at stress concentrators. These are engineering problems with known solutions you design. For the full temperature range, you choose materials with compatible thermal expansion coefficients. You use flexible joint designs. But the solutions have to be implemented correctly, across thousands of joints and seams and attachments, and maintained correctly across years of thermal cycling. The equipment on the surface, not inside the pressurized habitat, but exposed to the environment, faces this in its rawest form. Solar panels, antennas, mining equipment, rovers, power cables, anchors for structural tethers. All of it cycling through 500 degrees every 29.5 days. The design margins built into Earth-based equipment for most applications assume nothing like this. Equipment sent to the Moon has to be designed specifically for the thermal environment it will face, and it will still degrade faster than the same equipment would in a temperature-stable environment. Inside a pressurized habitat, climate control systems maintain temperature within a human-comfortable range. But the habitat walls are managing that 500-degree external swing while keeping the interior at comfortable conditions. Thermal insulation layers in the habitat wall do most of the work. Heating systems supplement during the long night. Cooling systems, possibly passive radiators, integrated into the habitat exterior, manage heat during the long day. The thermal management system is continuous and non-negotiable. A failure of the heating system during the 2-week lunar night, without quick repair, results in temperatures inside the habitat, dropping toward whatever the insulation ultimately allows. A failure of the cooling system during the long day results in the interior heating. Neither is safe. Both require redundancy. Both require monitoring. Both add to the maintenance load that the colony's crew has to manage, while also doing everything else. Everything described so far assumes the colony is already built. Getting to that point is its own challenge. The first humans to establish a permanent lunar outpost won't step out of a lander into a waiting habitat. They'll step out of a lander and they'll have to build one. Or, more precisely, they'll arrive to find some infrastructure already in place, pre-deployed by robotic missions that launched before the crew. And then they'll complete and expand it. This is the architecture model that makes the most sense, and it's roughly the approach both NASA and the European Space Agency have been planning around. Send robots first. Land prefabricated habitat modules and deploy them robotically, so when the humans arrive, they're not starting from nothing. The Gateway Space Station provides orbital staging, ISRU systems, in situ resource utilization, the technical term for using local resources, begin processing water and producing oxygen before the first colonists land. The first humans who arrive find a minimal but operational base. And then they get to work, building it into something more. But pre-deployment by robots requires that the robots work. Robotic systems on planetary surfaces have a mixed track record. Rovers and landers on Mars have broadly succeeded, but also failed, some immediately on landing, some after days or weeks, some after years. The lunar surface has hosted robotic missions with varying outcomes. Recent commercial landers have achieved partial success and outright failure. A habitat module that deploys imperfectly with a seal that doesn't close properly, a structure that's off-axis from its planned orientation. A solar panel that doesn't unfold may be unusable or require in-situ repair before the crew can inhabit it. The crew who arrives to find a malfunctioning pre-deployed habitat isn't stranded. They have their lander. But they have limited supplies and a deadline imposed by their own consumables. Repair and commissioning under time pressure, in spacesuits, with the tools that fit in the lander's payload, that's the scenario planners have to account for. And, as the colony grows beyond the initial outpost, construction continues. Adding modules, installing new equipment, expanding the agricultural section, building the storm shelter to the standard required for a larger population, excavating regolith for radiation shielding above existing structures. All of this construction takes place on the lunar surface, in spacesuits, with tools designed for the environment, by people who may have engineering training but are not construction workers. The learning curve is steep. The mistakes made in the early phases of lunar surface construction will be expensive and potentially dangerous. But they'll also be the foundation of the expertise that eventually makes it routine. Every skill that makes long-duration habitation possible, suit operations, surface construction, equipment maintenance, resource extraction, agriculture management has to be learned by doing it. There's no way to fully simulate it on Earth. The Moon teaches you things that a laboratory or a test facility cannot. And the first permanent colonists will be learning all of it simultaneously, under conditions where the consequences of getting it wrong are significantly higher than they would be in training. One question that rarely gets discussed openly, but that underlies every other one: who pays for this? The Apollo program, at its peak in 1966, consumed roughly 4% of the United States federal budget. In today's terms, that's somewhere in the range of $100 billion per year. It was sustained for about a decade, then wound down. The motivation was geopolitical, demonstrating technological superiority in the context of the Cold War space race. Once the moon landings were achieved, the justification for the expense weakened. Building a permanent lunar colony is a longer and larger commitment. It won't be accomplished in a decade. It won't be accomplished in 2. The resource investment required to go from the first permanent outpost to a self-sustaining colony of several hundred people is in a different category from anything any space program has yet committed to. The commercial model, the idea that private enterprise will build and sustain the colony because there's economic value, there is increasingly serious. Lunar resources are real. Helium-3. Though extracting and using it requires fusion technology we don't yet have commercially. Platinum group metals, which are rare on Earth and more accessible in some regions of the lunar surface where asteroid impacts have concentrated them. The water ice itself, as propellant, may be the most immediately valuable commodity. A fuel depot on the Moon means spacecraft don't have to lift all their return propellant from Earth's gravity, which changes the economics of deep space travel substantially. Rare earth elements, critical for modern electronics, are present in the regolith and may be economically extractable. Tourism, if the transport cost comes down far enough, represents a market. The economics of making lunar resource extraction commercially viable require transport costs to fall significantly below current levels. Starship and its successors may accomplish this, or they may not. The business case for early lunar operations is probably government-anchored national programs that provide the guaranteed revenue and the mission motivation to sustain investment before any private market develops. The commercial sector builds on top of that foundation, as it has with low Earth orbit services since the ISS demonstrated there was a sustained human presence to serve. The honest answer about who pays is probably governments first, and hopefully private enterprise eventually, if the transport economics improve enough to make resource extraction profitable. The full vision of a permanent lunar colony, one that sustains itself and grows independently, is a goal measured in decades, and investment measured in trillions of dollars across multiple nations. That's not impossible. Human civilization has made investments on that scale for things it decided were priorities. Whether lunar colonization reaches that status of shared priority across enough of the world's governments and commercial entities is a political and cultural question as much as a technical one. It's worth being honest about this. A permanent lunar colony could fail. Not fail in the sense of never being attempted, but fail in the sense of being attempted, established, and then abandoned, or failing more catastrophically, a systems cascade that the colony can't recover from. History has examples of ambitious remote settlements that didn't survive. The Norse settlement at Las Olmedos in North America lasted perhaps a decade before being abandoned. Greenland's Norse colonies survived for several centuries before eventually collapsing around the 1500s, probably from a combination of climate change, economic isolation, and conflict. Antarctic bases have been established and closed when the rationale for maintaining them faded. A lunar colony would be more expensive to establish, more technically complex to maintain, and more dependent on continuous external support than any of these. If the political will fades, if the governments and commercial entities funding the effort decide the return on investment doesn't justify the cost, the colony doesn't just struggle. It needs to be evacuated, or it faces a situation where the supply chain stops and the colonists have to survive on what they have. If it's early enough in the colony's development, before food self-sufficiency is achieved, That's a hard deadline. The colony lives or evacuates on whatever timeline its agricultural and resource production systems can sustain it. This is why the trajectory towards self-sufficiency isn't just an engineering aspiration. It's a survival strategy. A colony that can feed itself and maintain its own critical systems can survive a political disruption to its supply chain long enough to either re-establish supply or make difficult decisions about its future. A colony that cannot do these things is hostage to the continued goodwill of Earth. The design goal isn't just to build something that survives on the moon. It's to build something that can survive changes in Earth's priorities. That's a higher bar. And meeting it requires investing in self-sufficiency capabilities that might not seem immediately necessary in the early phases. The redundancy, the food production, the manufacturing capability, these aren't just nice to have. They're the margin that lets the colony persist if the external environment changes. Everything described so far is a single problem in isolation. The actual challenge is that none of these problems exist in isolation. Your water extraction system needs energy. Your energy system needs maintenance. Your maintenance program needs spare parts. Your spare parts were manufactured on Earth and must be shipped across 239,000 miles on a schedule that depends on launch windows, vehicle availability, and the continued commitment of the agencies or companies funding the effort. Your habitat walls are being abraded by dust, while your radiation shielding depends on them staying intact. Your psychological stability depends on food variety, which depends on agricultural success, which depends on water recycling, which depends on the same energy system that runs your water extraction from the polar crater. If the energy system degrades, the water extraction slows. If the water extraction slows, the agricultural system gets stressed. If the agricultural system gets stressed, the food supply tightens. If the food supply tightens, morale drops. If morale drops, the quality of maintenance work drops. If maintenance drops, the energy system degrades faster. These are not hypothetical chains. They are the design of life support systems, interconnected, dependent, fragile, in the ways that all complex systems are fragile. Pull one thread, and you feel it everywhere. The International Space Station is the most complex operational system humanity has ever built, continuously operated in space. It cost roughly $150 billion across all contributing nations. It houses 6 to 7 people at any given time. It requires a continuous resupply schedule to function several cargo missions per year, bringing food, water, equipment, spare parts, and consumables. It cannot grow its own food. It cannot sustain itself if the supply line stops. It is not a colony. It is an outpost with a permanent tether to Earth. A lunar colony, to be genuinely permanent, must sever that tether. Not immediately, early phases would be heavily dependent on resupply, just as the ISS is. But the trajectory has to point toward independence. The colony has to become, over years and decades, capable of sustaining itself without the continuous input of resources from Earth. The engineering complexity required to reach that point is not the sum of the individual systems. It's the product of how those systems interact. Every system depending on other systems. Every failure propagating through the interconnections. Every redundancy adding weight and cost that then requires more energy to support, which requires more reactor capacity, which requires more shielding, which requires more structural support. Nobody has built a self-sustaining extraterrestrial colony. Not even close. That's not a reason not to try. It's a reason to go in clear-eyed about what trying actually means, about the depth of commitment required, the investment necessary, and the realistic timeline between the first permanent outpost and a colony that could survive on its own. That timeline is measured in decades, possibly generations. None of this is speculation about the far future. This is work happening now. NASA's Artemis program is the most ambitious lunar effort since Apollo. Its goal is to return humans to the moon, this time to the South Pole, where the water ice and the peaks of eternal light make long-duration habitation more plausible. Artemis 1, an uncrewed test flight, flew in 2022. Artemis 2 carried a crew on a lunar flyby in 2026, setting a new record for the farthest humans have traveled from Earth. Artemis 3, which would be the first crewed lunar landing since December 1972, would place humans near Shackleton Crater. The Lunar Gateway, a small space station to be assembled in lunar orbit, is being designed as a staging point for surface operations, a relay for communications, and an emergency refuge. Commercial lunar payload services contracts have already delivered scientific payloads to the surface with mixed but real success. The Intuitive Machines mission in 2024 became the first American spacecraft to land on the Moon since Apollo 17. It landed at a slight angle but returned data. Progress. China's Chang'e program has been steadily advancing. Chang'e 4 accomplished the first ever soft landing on the lunar far side in 2019. The far side had never been visited by any spacecraft before, not even a lander. Chang'e 5 returned lunar samples to Earth in 2020. The program is building toward crewed lunar missions in the later part of the 2030s. China has not signed the Artemis Accords, the framework agreement that 68 nations have now joined to establish behavioral norms for lunar activities, including transparency, interoperability of systems, and coordination around historic sites. Russia hasn't signed either. The South Pole water ice that makes permanent colonization viable is the same region that both Artemis and Chang'e are targeting. The resource and territory questions that have so far been managed through treaty frameworks designed for a less capable era of space exploration are becoming more immediately relevant. On the commercial side, SpaceX's Starship represents the most significant shift in launch capability in decades. Its design payload capacity, potentially 100 metric tons to low Earth orbit, with significant capability for lunar delivery, changes the economics of getting mass to the Moon in ways that earlier vehicles simply cannot. Every previous lunar architecture has been constrained by the weight limits of what rockets could lift. If Starship fully achieves its ambitions, those constraints change fundamentally. The cost per kilogram to the lunar surface has been falling. It will continue to fall. The legal framework governing all lunar activity remains genuinely unsettled. The 1967 Outer Space Treaty, which forms the foundation of space law, prohibits any nation from asserting sovereignty over the Moon or any celestial body. No country can claim the Moon. What the treaty says very little about is resource extraction, property rights in the context of extracting but not claiming territory, the governance of permanent settlements, and how to handle disputes between actors from different nations operating in the same region. The Artemis Accords, signed by 68 nations as of 2026, attempt to fill some of these gaps. They establish principles around transparency, peaceful operations, registration of activities, and the concept of safety zones around operations. But the accords are not a ratified international treaty. They're a political commitment. And China and Russia, who will have their own lunar programs and their own interests, aren't party to them. The governance structure for the moon in 50 years doesn't exist yet. Whoever builds it will be making decisions with consequences that outlast everyone involved in making them. The technical progress is real. The policy infrastructure is lagging. Both need to advance together. Here's what the moon is actually asking. Every challenge described tonight, the pressure, the water, the radiation, the dust, the gravity, the food, the medicine, the psychology, the power, the materials degradation, the systems integration, the legal ambiguity, every single one of them is a problem that Earth solves for you automatically. You breathe because the atmosphere exists, maintained by billions of years of plant life and geological cycling, thick enough to absorb radiation and burn up space debris and moderate the temperature between night and day. You drink because water cycles through rainfall and rivers and aquifers, powered by the sun and moved by gravity. You eat because topsoil took hundreds of millions of years to develop from bare rock into the rich living medium that allows agriculture to exist. And because life evolved over billions of years into the ecological web that makes the food chain possible, you walk outside because a magnetic field generated in Earth's core and 65 miles of atmosphere stand between you and the full lethality of space. You survive because this planet was built over 4.5 billion years to support exactly the kind of life you are. Not built for you, exactly you evolved to fit what it already was. But you fit it. Precisely. Every feature of your biology is calibrated to this specific gravity, this specific atmospheric pressure and composition, this specific radiation environment, this specific light cycle. You are an Earth organism. And Earth is your life support system, planetary scale, running for free, and you don't have to maintain it. The moon offers none of that. The moon is what the universe looks like in the absence of 4.5 billion years of biological and geological preparation. It is the baseline, a rock in space, honest about what it is, not hostile to you, exactly. Indifferent, which amounts to the same thing. When you understand that, the question changes. It's not, can we colonize the moon? The engineering answer, given sufficient time and resources and commitment, is probably yes. The question is, what kind of civilization does it take to do this? What level of technical mastery, organizational capacity, resource investment, and sustained commitment across multiple generations does it require to build a self-sustaining community on a world that did not prepare for you? What does it mean to live somewhere that gives you nothing for free? Everything that Earth gives you, freely air, water, food, protection you have to build. You have to build it precisely and maintain it indefinitely, and you cannot afford to get it wrong. The moon is 2 light seconds away. It's the nearest thing in the cosmos. If we can't do it there, we can't do it anywhere. If we can figure out the dust and the radiation and the food and the water and the gravity and the governance and the medicine and the psychology and all the ways they interact and compound and fail together, then we aren't just a civilization that went to the moon. We are a civilization that learned how to leave. The difference between those two things is the difference between exploring a place and becoming capable of existing somewhere that was never made for you. It's the difference between a visit and a future. We have been visiting. The question now is what comes next. It's also worth being clear about what the goal actually is. Not the operational goal that's well defined. The deeper goal. A self-sustaining lunar colony isn't an end in itself. It's a proof of concept and a stepping stone. If humanity can build a community that survives indefinitely on a world it didn't evolve on, that's not just an achievement in lunar science or space technology. It's a demonstration that we can do it. That the biology, engineering, psychology, governance, and resource management can be made to work together in an environment without Earth's 4 billion years of preparation. The Moon is the easiest place to make that demonstration. 2 light seconds away. 3 days by current transit. Close enough for real-time communication. Close enough that a resupply or evacuation is feasible if something goes badly wrong. The lessons learned on the Moon about ISRU, about closed ecological systems, about human physiology in partial gravity, about the governance of isolated communities, about what it costs in engineering and resources to keep people alive somewhere hostile. Those lessons are the curriculum for Mars. And Mars is the curriculum for everywhere else. The solar system is old enough that if we're patient and systematic and willing to invest, we could eventually have communities on multiple worlds. Not in this century. Probably not in the next one, for most of those worlds. But the direction is toward expanding the envelope of where humans can live. And the envelope expands by learning. You learn on the Moon. You apply those lessons to Mars. You apply what you learn on Mars to the asteroid belt. Each step makes the next one less likely to fail catastrophically. The Moon isn't the destination. It's the first real test of whether we can become a spacefaring species, not in the sense of launching ships, but in the sense of actually living out there. Of building communities that don't require Earth to function. Of producing children on another world who grow up thinking of that world as home. That's what permanent means. Not visiting. Not outposting. Home. There's a boot print on the Moon right now. Gene Cernan's. Left in December 1972, the last time a human being walked on the lunar surface. The last footstep on another world, placed by a man who said, before climbing back up the ladder, that he believed history would record that the challenge of his time had forged the destiny of tomorrow. He expected us back not too long into the future. It has been more than 50 years. Because the Moon has no atmosphere, no wind, no rain, no flowing water, no biological processes, no erosion of any kind, that bootprint looks today exactly as it did the moment it was made. The dust settled around it and hasn't moved. The impression in the regolith is as sharp as the day it was pressed into place. It will look the same in 1,000 years. It will look the same in 1,000,000. The Moon preserves everything. It preserved the challenge, too. Every problem described tonight has been waiting on the lunar surface since the Moon formed 4.5 billion years ago. The dust has been sharp since the first meteorites started grinding the surface. The radiation has been falling unimpeded since the Moon's magnetic field faded billions of years ago. The 2-week night has been cycling since the Moon became tidally locked to Earth. None of these problems are new. We just weren't in a position to care about them before. We sent 12 people. Each mission lasted days. They conducted science, planted flags, collected samples, deployed instruments, and came home. They left boot prints. The boot prints are still there. The next chapter requires staying. And staying requires solving everything described tonight, not in the lab, not in principle, not in a proposal, but in practice, on the surface, for decades. That's harder than what the Apollo program did, by a significant margin. It's also more important, because a civilization that can build a self-sustaining colony on the moon has answered a question that matters for a very long time. Are we capable of living somewhere other than Earth? The answer to that question determines what the future looks like. Not just for the people who go, for everyone who stays, for every generation that follows. The moon doesn't meet us halfway. It never has. Everything we've ever gotten from it, we had to go get. That's always been the point. Good night.